So as I said, you shouldn't use list for computing. So what should we do? Should we use instead? And the answer to that is that we should use something called NumPy. And NumPy is it's not part of Python yet, at least. It's a very powerful library for doing computing on large set of floating point or arrays of the same data type. And we will go through how you will work with these in this chapter here. So the module is imported like this. And this is the standard convention of importing NumPy. So you will see this in multiple examples. And the reason we do this is because NumPy actually provides a lot of the mathematical functions that are part of the Python math library. And we don't want to clash with those, because the ones in NumPy are better and used for arrays. So usually what you do is you import it as NP. And then all the NumPy functions will have NP as a prefix. So this, you could also use this here to import, but this is not recommended because that will replace all the math functions from the math library or clash with them in different ways. The basic object in arrays is the array object, and that is what you will work with. That is the class that implements all the array operations. You can create new objects by calling the mp.array function, and it consists of two parts. First, you will give the values of your array. You can do that as a list. You can have if you have a two-dimensional array, you give it as a list of lists and so on. The second parameter is optional. It's the data type. So in NumPy arrays, you actually always have to specify, not always, but all elements in an array will have the same data type. And if you don't specify the data type I'll show here, it will figure the data type out of what the data type in the lists are. So here you get, okay, I forgot to import it, like that. So now you see I specify float, and if I print the array just with a print statement, you can see here that you have a decimal dot, and that means that I have actually floating point values in my array. However, if I just provide a list with integers, I will get an integer array. So it looks at what you are giving it and determines the data type from that. Same thing if you give a list of floating points, it will be a floating point array. Multidimensional arrays, as I said before, you can give these as linked lists. So if you want to give a two-dimensional array, you give first row, second row. So here you have outer list here, and then you have the first row, second row. And you can see also when you print NumPy arrays, they will actually print it with the dimensions that you have given them. So a two-dimensional array will print it on 2 rows. And so on. So you will, it's the same thing if you have been using MATLAB. You will see the array structure and it prints out the structure of the array as well. So how are arrays stored in memory? This is perhaps not, if you just work with Python, you probably don't have to think too much about this. But Python is used, for example, with Fortran and C. And you need to know about these things because by default, NumPy uses the C ordering of arrays. And that means that arrays are created row-wise. Because in memory, in the computer, nothing is two-dimensional. You will allocate memory and you get a really long array of data that is stored sequentially in memory. So the two-dimensional part is kind of how you get through the next row, the scheme, how you move in your single data. And in C, you allocate a single row, and then you go the first row like this in memory. So this here, array A here, the data here is actually stored in a single row in memory. going from row by row like this. This is in Fortran is the other way around. Then you go column by column. And that is something you need to remember. If you call a Fortran library with a Python array, you need to tell Python to actually allocate in a different way. Or you have to do a reshape, which is costly. Then you can actually allocate your arrays directly in the way you want it to be. So you can allocate the Fortran array basically by specifying a special format. But I'll come back to that later. Array properties. So when you have created an array, you can check some properties here with using attributes. And one of the attributes is the shape attribute. And that gives you tuples of the dimension. So in this case, I have a one-dimensional array, and it returns you a tuple with a single value with 4 elements. B is a 2-dimensional, it has 2 by 2. And C is a 3-dimensional array, 2 by 2 by 4. So shape is a good way of querying your created arrays. One way you can use this is to actually, if you want the rows and columns of an array, you can do r, c equals to b.shape, and it will kind of assign those variables directly in a single line, like that. There is also an attribute of the number of the dimensions of the array object, and that is called ndim. So there you can see that they're not following the PEP 8 standard for variable naming. But anyway, it's an old Python. NumPy is quite old. So in this here, B has 2 dimensions. And there are some other properties that can be good to know as well. So you have shape and ndim. There is a d-type property, which gives you the data type of your array, what the data currently is stored in. Dot size, the total number of elements in the array. And you can also get item size, and that is the number of size of an element in bytes. So for example, if you're storing floating point, we can see, we can run this here. So you can see I have data type is an integer 64, and the number of elements is the size is 4, and each item has 8 bytes. And in 64, that is 64 bits, and that is 8 times 8. So every integer takes up 8 bytes. And if we would have done, for example, by it's the same size here, so you can float 64. That is a 64 bits floating point. Each item, there are 4 items, and each floating point takes up 8 bytes, and that is corresponds to a double precision floating point in Fortran, or a real 8 on an x86. So 8 bytes. That. So by default, Python uses the double precision floating point. You can change the shape of an array, and here we have to kind of reshapes the array with preserving the number of elements in the array. And that is actually not a costly operation, it's just a way of looking at the array. So it's not, and to kind of illustrate this, I create a function called memory of A. Ignore this thing here, it's just going internally in the array, but it will return you the memory address of that array. So in this case here, we have created a 2 by 2 array. And then we print the memory address of A. In this case, you can see it's 65792. And then I create A flat equals MP reshape of A. And then I say I want to be 4 by 1. We print that, you can see here that it's 4 rows, 1 column. But interesting enough, you can see it's the same memory. So NumPy goes to really great lengths to avoid copying, because it's really inefficient to copy large arrays. But reshaping is just, you view your array in different ways, and if you do that without changing the number of elements, it's simple operation. But also to be aware that the reshape operation here returns a view of the A array. So we can see here that if I changed the first row and first column of A, that will actually change both arrays. And this is something you need to remember, because this is a common mistake you do when you're working with NumPy, is that you expect it to be a copy. And as I said before with lists, there is a copy method here as well. So you can do C equals to A.copy. And you can now see here that there are different arrays now. And also you can see the memory locations are different. And some other examples here. So you can see here that I have an array here with 8 elements. I can reshape it to a one-dimensional array. I can reshape it 4x2. I also note that reshaping is not the same thing as transposing. So if you want to transpose of an array, there is a function here called NumPy.transpose, and that actually transposes the matrix as in linear algebra. Let's have a 10 minutes break. Then I continue. So reshaping is one point. Then we reshape an existing array. Don't change the number of elements, but you can also change the size of an array. And resize will do a reallocation of memory. So it's a kind of a costly operation. And here you can see here that if you have a 2x2 from the beginning, if I do resize, it will actually copy the values over from the other matrix and fill it out with values. So nothing changed here. There is also a way of adding, sometimes when you have arrays that have only one dimension, you want to kind of pass it to something that has more dimension. There is a special attribute you can add that will add a new axis to an existing object. So in this case, you have an array of single dimension 1, 2, 3, and I want it to be a row array or a column matrix. You can do that by adding in the axis you want to. In this case here, it will be a single row item, and then in this case I will add columns here, and then I get the column vector here as well. This is kind of a convenience thing if you want to go from a single dimension array to a two-dimensional array. You can just specify that by adding this attribute in your array declaration. Now we have kind of manually created arrays, but sometimes, I mean, if you are working with arrays that are 10,000 rows or columns, you obviously don't create them by specifying a list. It's a bit complicated. So what you can do then, there are some functions that can create arrays that are filled with zeros, and that is the zeros function. Probably comes from MATLAB. It will create a zero array with 5 by 5. You can, of course, it has the same arguments as the array function, so you can specify a data type here as well. The default is floating point. If you specify int, you will get an integer array. There's a similar function called ones that will create an array with only ones in it. And you can, this is something, if you want an array filled with a certain number, what you can actually do then, you can do mp1s, the size you want, and multiply by the value you want to have in it, because it contains ones, and then the multiplication operator will be applied on each element in the array. So in this case, you will get an array filled with 42. You can also use create ranges of you can create a range of range array, and that works just like the range function in Python. So you can give it a starting point and an end point, and then you get an array back. So in this case here, I want to create an array range that is 10 elements going from 0 to 9. Looks like this. So that this is the equivalent of using the Python range, but in this case you will get a NumPy array back instead. You can combine a range with reshape to quickly create arrays of a certain dimensions. In this case, I want to create an array that has values from 0 to 99, and I want it to be shaped 10 by 10. So then I do NumPy reshape array 100. Of course, you have to have 100 elements to be able to reshape it to 10 by 10, but then you get something like this. And here you can see reshape doesn't do any, it's not a costly operation, it's just a reinterpretation of the single dimension array in this case. And just like the range function in Python, you can give it a start and end point. So here I give it going from -10 to 10, but not including 10. The data type float. You can see here it goes from -10 to 9. I can have a step length here as well, and then you go in steps of 2. In this case, it will be an integer array. Yeah, you can specify the data type here as well, and then you get floating point instead here. You can also create identity arrays by using the identity function. So I mean you get ones on the diagonal, like this. It's tempting to use the A range to kind of give values that you want to do for plotting, for example. But there is a much better way of creating linear ranges, and that is actually using the linspace function. So in this case, you can say, I want to go from 0 to 1, and the second parameter, that value will be included in the range. So there is not a less than or something. It will guaranteed be included. And then you can say, I want 10 values. Same thing you can have, so you can have 20 here, and you get it will create a linear interpolation between those values. And that is, if you want to plot function, you can use this to kind of have the x dimension, then you can create an expression, x equals to something, and then you can use that as an input. Yeah, then you can do operations on arrays, of course. And so if you add and subtract to an array, so if you do +3, that means it will be an element with addition. So 3 will be added to all elements of the array. Same thing with subtraction, like this. Now here we're coming into this. Arrays are not matrices in a mathematical sense. They are just arrays of numbers. So operations here by default are element-wise. So if you do A times 3, it's an element-wise multiplication. Same thing with division. You can also create an array, negative array, by doing putting a minus sign in front of it, and then it will get all values will negate it. When you have important NumPy, most of the mathematical functions are available in the NumPy library. And when you call a function with an array, it will compute the function on all values in the array. So if you do print np.sin, you will get an array that has computed sin on all elements in that array. And there is a link here to all the functions in the NumPy library. And that is the reason we import as np, so that we don't overwrite the math functions, for example. In Python, we don't handle arrays. Operators, adding two arrays at an element-based addition on the two of them. And actually, they don't have to be the same. So if you have a smaller array, that will be repeated in the larger array. So in this case, you can see here I created an array 1, 2, 3, and then I have a 5 by 3 array with ones, and then I add a plus b, and you can see here that it repeats add that row to each of the elements in result. So what if you want to do matrix multiplication? We create new operators, of course. So matrix multiplication, there is you can use the @ operator. That means matrix multiplication. You can also call the .np matmul function to do matrix multiplication. So like this. Yeah, broadcasting rules. That is how you. What happens if there are different sizes of dimension, and we already saw that here that if an array has different number of dimensions, the small array will be padded with ones on the left side. If arrays have different sizes, then they will be stretched. These are some examples here. This is a plus b. So in this case here, the b value will be broadcast and added to all of the elements. I already showed this. It's just kind of examples of this here. We'll skip that there. And go indexing. So indexing is slightly different than nested lists. So you use the bracket operator in Python, and you give it rows and columns separated with a comma. So if you want to access the third element here, you do a bracket and the element you want to access. Also note that Python arrays are zero-based. So if you convert from a MATLAB code, for example, you have to really be careful how the indexing are. In MATLAB, it's one-based indexing. So I have to think about converting code from MATLAB to Python because it's not the same. Assigning array elements is just the same like using list. You just give here, I want to assign the third element in A value 42. That's done. If you want to do a two-dimensional, you do 1,2 and then the number. And that will be inserted in the array. There is no problem mixing lists and arrays. So if you want to assign a row in B certain values, you can provide a list. So this is a list, and NumPy has no problem taking that as an input and assigning that in expressions. You can also do it, in this case I will go for here, this is the third column, all rows, and I assign a list to that one here as well. So you can see here that here I have 42 here, and I have 42 in this direction here as well. So mixing lists with arrays is no problem. Sometimes if you get into too large lists, it's probably better to use arrays directly, because then it doesn't have to make any conversions in that sense. Then we come into this part where you can access parts of an array, and usually that is called slicing. And it's very similar to what you do I showed you with lists yesterday, that you can give a colon, then you get everything, and you can use start and end point. So here you can do extract a start, that is from the values of the start up until end -1. Starting point to the end, values up until the end -1, and all values. So here you can see that I can do 1.5 here. I can do 5 colon. I can do colon 5. Like that. Here we go back to this views and copies. So when you do a slice, as usual, NumPy will try to avoid making copies if not possible. So a slice is usually a view of the original array. So if you change the slice, it probably will change the original array as well, where you sliced it from. And we can see here an example here. We have here a range here, going from 0 to 24. We have a memory location here. We can print the data of A here, like this. And then we do B equals to A1 to 5. We print B. And we can see here that, yes, the location is a bit different, but there is the data property of an array is actually memory pointer in memory. And you can see they actually belong to the same memory block. So that means that if you change something in B, A will also be changed. So you can see here I changed something in B, it's also there. So that is also something to think about. If you really want to make sure that it's unique, use the copy method so that you get a copy of the array that you slice. But usually, if you're working with large array, this is probably what you want. You want it to be memory efficient. So you don't want to do any copy or reallocation, but that are expensive operations involving the operating system. So if you should work on the data that is already there. Here are some examples here. Here are all except for the last, second last. You can also use -1 just to really for list, then you get the last element of A. You can have a step part here as well. And you can reverse it here by using -1 as a step size, and you get the reverse of the element. And you can do the same thing here with the two-dimensional arrays. And then you can get, for example, all rows using the colon notation. It's very similar to MATLAB. You can use -1 to get the last column or last row, for example. That's you can use this notation here to get every other row in an array. There are some other interesting things you can do. There is something called Boolean indexing. So let's start to create an array here. So this is the original data array. So what we can do here, we can create a mask. And that is kind of a criteria for what we want to create. So data equals to greater than 0. And what we get then is we get the Boolean array where this condition is fulfilled. And we can use that to extract values. So we can put that mask into an indexing, and then we get only the positive values from that array. We can do really complex things, or really interesting thing here. Here I do data.copy. I don't want to change the original array. Data copy less than -1 equals to 1. And then we can clip the values to below -1. You can see here. You can see here that we put this -1 here in array instead. And you can do extreme things here with that. So, and the thing is that when you're using these things, you're using the internal implementation of NumPy, which is implemented in C. So usually you get quite fast speed up if you do this, instead of using loops where you go through every element and you do these things. That is really slow in Python. So these things can speed up your code significantly. Fancy indexing is a kind of strange word, but it's when you are using arrays to index other arrays. So let's first create an array here. We can create an index array, and then we can use that to index another array. So here we extract 0 to 4 rows here. So we get 0 and 1, 2, 0, 1, 2, 3, 4. 2, so that's 8, 9, and then we get 4, that is 16, 7, 8. So it's really a nice way to do. You can also do in 2 dimensionals. So here you have an array that's 0, 1, 2, 1, 2, 3, and then we extract the row indices and column indexes of the original array, like that. We can do more things here. I'll go through extract details here. So here you have basically you go into and extract another 2-dimensional array using these indexes here. I've gone through that again. That is more in detail. Yeah, that is what I explained before here. You have row major and column major. So C is row major. That is, you go row by row, and Fortran you go column by column. And you can then actually check. You can convert between them. Sorry. So I have here an AC here. So by default, everything you create in NumPy will be let's see, row major. Like I can see. But you can convert an array as Fortran array here. And then you can use them as a normal array. You don't have to think about anything. You just create it in this order. And the only thing, the only reason to do that is when you want to call something that is a Fortran array. And sometimes also it can be useful if you are iterating in a certain direction in an array. That it can be benefit if you're going column-wise, that you allocate an array in the column major way, because then the caching of the processor reads ahead, and if it's column order, it reads ahead in the same column. So that is something that can be useful as well. Here are some performance checks here that you can see how that works, but you can run them yourself. This I covered already. There's some in how you memory allocation. Yeah. So then we have some methods on it. As an array is an object, it has a lot of methods connected to that object, and some of them here can be quite useful. So if you have an array, you can create the total sum of the array. Now you can do that either using the method connected to the array object, so a.sum, but you can also do np.sum. So there is usually a corresponding function in the NumPy library that can do the same thing as the method. So just here you call that method on the object, and here you call the function on the object. But it gives you the same result. You can sum only the columns. So if you put a parameter on sum, you will get the column sums. If you put a 1, you get the sum of the rows. Same thing, there is a product function. Works the same way as for the sum, but it calculates the product instead. Okay, so I don't know if you have worked with NumPy before, but there was a matrix class in NumPy. And up until the last part, I actually gave a talk about the matrix class, but it's deprecated. And I was hit by that in the library. I did that all of a sudden they removed matrix class and in NumPy 2. So if you have matrix, you need to rewrite that. I'm not sure why they had to deprecate it, but anyway, it was always 2-dimensional, of course. It had confusing behavior differences from arrays. The multiplication operator meant matrix multiplication. I thought that was for writing expression. It's more, yeah, it looks better, but I can understand the problem with that the multiplication operator on array is different from the matrix multiplication operator. So that's why they kind of want to differentiate with that. But basically, you can do the same things with, and here's some illustration how you can do that. And there is still a method called transpose. So you can do a.t to get the transpose of an array. So it's not totally. And then you have to do this instead of the normal matrix multiplication you did before. But basically, beware of that. There was a matrix class, and it's not there anymore in NumPy 2.0 or up. Here are some examples of what you can do here. So here you can do m times m.t. So here you can see you use the at operator for the matrix multiplication, and we use the .t here to get the transpose of the array instead. You can calculate the eigen vectors values. There are many of these built-in functions in the library. That doesn't require you to use the matrix class here. We have the norm functions here as well. And here are some guides that you can have for converting the modern Python. So a times b, matrix multiplication, is a at b, or np.a, b. A.I was the inverse of the array. That is, we have to call np linalg.in a. A.t is preserved. A.h is a bit different here. Inverse a. So there was some kind of, so these things are from the matrix class, and this is what you need to replace it for. So use the at operator now in the future. Be explicit of the dimensions, and use reshape when you don't want to change the number element. Use the linalg functions for advanced operations. Yeah, use the proper solvers. That's obvious. You can see here some example how you can use this. I will leave that exercise to you. But I will go through in the end here reading and writing arrays. So I told you about reading and writing files in the previous lecture. That is probably not suitable when you have large arrays and you want to write them. So there are built-in functions in the NumPy library for writing large arrays to disks. The easiest way is just doing save, the file name, and your variable. That will create a file and write that down to disk, and you can read that back again using load. So you see here, if I run this, I get two files here. You can read them back again, just mp.load. So it's similar to the math files in MATLAB. And you can run them here again. Doing plotting like that. But what if I want to write, I don't want to have a single file for every array. You can do that as well. So you can do an xy.dat file, for example. You open a file with a file object in Python. And then I can, the save option, if you don't give a file name as the first argument, that you can give it a file object. And then you can give your arrays as a second parameter. And that will first save the first array, and then we will continue saving the second array in the same file. You need to specify the binary part here. So VW binary stands for write binary. Because the save and load files, they will write the NumPy array as binary files. So it's a quite efficient way of writing your arrays to disk. So now I will have a xy.dat file. If I want to read it back again, I do it with read binary, and then I do load x, load y. And then I can show that you read it back from disk. So that's the way. So for example, if you have a long-running calculation and you want to save the state of all your arrays, you can use load and save. And you save that to disk, and then you can read it back again to continue your calculation, for example. Then finally here I will go through some ways so you can solve your solving equation system. So the most common one, a equals b. That is part, you find that in the linalg module of NumPy. There is a solve routine there. So basically you create an array here, I create a result vector, and I do linalg.solve like this, and then I get my x vector here. And then I can verify the solution as well. And also the solver will throw exceptions. So you can, if you get a lin-alg error exception, the matrix is singular and cannot be solved. So this is a good defensive way of writing a solver like that. You can solve overdetermined systems. That you do with the least square method here. Underdetermined you can solve as well. Use the same function there. And you can do, I just gave you some examples here. So there is a lot of functions built into the NumPy library for doing this. And this is not a course for teaching numerical solutions here. I just give you the way those functions are there. Something I kind of touched upon before is that that you should try to avoid loops whatever you can. So loops in Python are really slow. But if you can mostly avoid using loops in Python by vectorization. So basically you kind of try to create an expression, single line expression that calls NumPy functions in different ways. And NumPy functions are all implemented in C, and in many cases they're also implemented using math kernel libraries that are really efficiently implemented. So they can also use multiple cores if you use as well. So here are some examples. Here we do the pure Python approach here to different things, adding, removing, and we do some performance comparisons here. And let's see if we can run this. The exact numbers you can kind of ignore, but you can see here that the pure Python method of addition took 361 milliseconds, vectorized 5 milliseconds, square root 95.26, number vector actually had to, there is a bigger array, but it did it in 1.88 milliseconds. Complex operation, same thing. So NumPy is 10 to 100 times faster than normal Python code. So always try to use the vectorized versions of and use the NumPy functions and avoid loops. Sometimes if you have an iterative method or something, you need a loop, but then make sure that the methods inside the loop are vectorized. So the big chunks of operations are using the NumPy functions. Here are some exercises you can try yourself when you get home as well. So this is what I wanted to take up today.